Hello, welcome to the Recitation week 13. Today I will be doing a brief review, so I will be solving some problems uh, in a broad topic related to what you have studied in the class so far. So let's do it. I have 5 problems in total, and the first problem is related to the Laplace transform. So I have a function in time domain f of t given as follows. So e to the power of 2t times t cubed plus 5t minus 2 cosine pi over 4 times t. And the problem here is we need to find the corresponding Laplace transform. So we just need to apply the Laplace transform. So Laplace of f of t is Laplace of e 2t times t cube. So let me write it this way: t cube e 2t. Since Laplace transform is linear, then we can separate them. 5t e 2t, and then the last term we have minus, so minus Laplace 2e 2t cosine pi over 4t. Okay, so we can directly use the Laplace transform table. So for this term right here, we have 3 factorial over s minus 2 in parentheses and take it to the power of 4, because 3 plus 1, and 3 factorial is 6. Here is we have 5 times 1 factorial over s minus 2 power 2. Okay, so that's just 5. And then right here we have minus 2, and from the table we have s minus 2 squared plus pi over 4 squared, and then here s minus 2. Okay, so that's the answer. This is equivalent to f of s. Now problem number 2. Here I have a function in Laplace domain 3s plus 5 s squared plus 2s plus 5, and the problem here is to find the corresponding function in time domain. So we need to use the inverse Laplace transform. So hopefully you guys still remember the partial fraction expansion. So we need to use that to factorize this fraction of polynomials. We know that here s squared plus 2s plus 5, they have complex roots. So to make it easier, then we do not need to separate them. So the partial fraction expansion of this term here is a over s plus, keep the denominator s squared plus 2s plus 5, and since this is a second degree polynomial, then on the numerator we have b s plus c. Then we need to find these coefficients a, b, and c. Okay, so let's do a very simple algebra. So we cross multiply a times this term s squared plus 2s plus 5 and plus s times b s plus c. So a times s squared plus 2s plus 5 and then plus s times b s plus c, and then we have the same denominator, s times s squared plus 2s plus 5, and then on the numerator we have a plus b s squared plus 2a plus cs plus 5a. Okay, we from here we know that a plus b is 0, 2a plus c is 3, and 5a is 5. So from here we know that a must be 1. Then since a is 1, then from here b should be minus 1, and since a is 1, then 2 plus c equals 3, therefore c is 1. So f of s can be written as 1 over minus s minus 1 over s squared plus 2s plus 5. Also, this can be written as 1 over s minus 1 over s plus 1 squared, right? Because s plus 1 squared is s squared plus 2s plus 1. So we have 4 as the remainder, and 4 is 2 squared, so 2 squared, and then we have s plus 1, as we have minus 2 there, right? Because s plus 1 minus 2 equals to s minus 1. Okay, so we can expand this s plus 1 over s plus 1 squared plus 2 squared, right? And then plus 2 s plus 1 squared plus 2 squared. Then we can use the inverse Laplace transform table, so that 1 over s is the unit step 1, and then here is e to the minus t, and you have sine of 2t. Here is plus e to the power minus t cosine of 2t. Okay, so this should be the f of t, which is the inverse Laplace of f of s, and that's the final answer. Okay, let's move on to the next problem 3. This time we need to solve the ordinary differential equation y double prime t plus 15 y prime t plus 56 y of t u of t, given that u of t, the input, is a step with the value of pi, and initial conditions it's given, so y of 0 equals y prime 0 equals 0. Okay, so let's apply the Laplace transform. Y double prime t plus 15y prime t plus 56 y of t, and then Laplace of pi. Okay, we have y of s, and then s squared plus 15s y of s plus 56 y of s, and then pi is a step function, so you have pi times 1 over s. Okay, and we can write this as y of s equals to pi over s times s squared plus 15 s plus 56. Okay, so to solve this ODE, then we need to find y of t, right? The solution is y of t, so we need to use the inverse Laplace transform. But to solve it, then we need to apply the partial fraction expansion again. So the partial fraction expansion, we have, so this polynomial s squared plus 15s plus 56 actually can be simplified into two terms. It's a quadratic polynomial, so we have 56 is 7 and 8, right? Yes. Okay, so since the roots are all real, so we have a over s plus b over s plus 7 plus c over s plus 8. To find a, so we can multiply s with y of s and then substitute s with the root 0. So pi over s plus 7 s plus 8, and substitute s equals 0, we have pi over 7 times 8, 56. B, we have s plus 7 y of s, substitute s with the root, which is negative 7, and we have s over s plus 8, substitute s with minus 7, we have pi over minus 7 times minus 7 plus 8 is 1, so minus pi over 7. Last one, C, we have s plus 8 times y of s, and then we substitute s with negative 8. We have pi over s multiplied by s plus 7, and then replace s with negative 8. We have pi over minus 8. This is minus 8 plus 7 minus 1, so pi over 8. Okay, so we have pi over 56 over s, and then minus pi over 7 s plus 7 plus pi over 8 s plus 8. So y of t is the inverse Laplace of y of s, and this is a step function, so pi over 56, and here we have pi over 7 e to the power minus 7t plus pi over 8 e to the power minus 8t, and that's final solution. And this is for t greater than or equal to 0. I think this one is 2. Okay, so that's the solution of this differential equation. Okay, next problem. So this problem, it's quite complicated, so we need to determine the range that makes the closed loop system to be stable. We have a system given by this transfer function. G of s is 1 over s to the 4 plus 10 times s cubed plus 20s squared plus 20s minus 3. Then we have another system, 13 plus k over s, and k is required to be positive. And here is the transfer function we have designed already. C of s, so C, usually C represents the controller and G represents the plant, the system that we want to control, and we have a negative feedback, the output here. Okay, so basically we need to use the Hurwitz criterion or the root table to determine the range of k that makes the closed loop system stable. Right, so first step is, of course, we need to compute the closed loop transfer function y of s over u of s. Since we have negative feedback, then you should remember that the transfer function is given as c of s times g of s over 1 plus c of s times g of s. Okay, so it is equivalent to 13 plus k of s to the 4 plus 10s cubed plus 20s squared plus 20s minus 3 plus 13 plus k over s. So we can simplify this into 13 s plus k, and then here is s to the 5 plus 10 s to the 4 plus 20s cubed plus 20s squared plus 10s plus k. Okay, now that we have the expression for the closed loop system, then we can construct the root table. It's a 5-degree polynomial, so s to the 5, s4, s3, s2, s1, s0, and write the coefficients of the denominator: 1, 10, 20, 20, 10, and k. Here is 10 times 20 minus 1 times 20, so 9 times 20 over 10, so 9 times 2 is 18, and this term here is 10 times 10, 100, minus 1 times k, so 100 minus k over 10, so 10 minus 0.1 k, here is 0. Here is quite complicated, so let's put x there, and then we compute x is what? It's something divided by 18, right? So 18 times 20 minus 10 times 10 minus 0.1 k. Okay, so you can simplify this. I got 260 plus k over 18, right? Here is just k. How about this term? This term is let's say y. So we need to compute y. Y is what? Y is x, right? X times 10 minus 0.1 k minus 18 k over x. It is equal to 10 minus 0.1 k because x cancels, minus 18 squared k over 260 plus k. And this term here is y times k, so you have 0 there, right? So y times k minus 0 over y is k. Okay, we know that we need k must be positive, x must be positive, and y also should be positive to ensure that the closed loop system is stable. Okay, k greater than 0, that's easy. How about x? So we know that x is 260 plus k over 18. So x is positive when 260 plus k is positive, or k is greater than minus 260. But since k must be positive or greater than 0, then this condition is doesn't matter. So we can neglect this condition because this condition is not important because we need k to be positive anyway, right? So just uh, abandon it, remove it. Now we have y, which is on that term right there. Okay, observe that since we need k to be positive, and from x to be positive, we know that 260 plus k also should be a positive number, then 260 plus k always be positive, right? So we can multiply y with 260 plus k. So 260 plus k times y, we have 260 plus k times 10 minus 0.1 k minus 18 squared k. And this should be also positive, right? um this is equal to this polynomial, or so we can simplify this into 555 k squared plus 188.88 k minus 144.44, and this will be negative. This can be factorized into k plus 347.66 k minus 7.48. This will be a negative. So we know that so we have a real line. This is the real line. This point represents minus 7.48. This point represents 347.66. So you have three region here. Say k is 0, so 0 is somewhere here, right? If k is 0, then we have negative, so obviously this is the region that satisfies this condition. So we know that k must be between minus 7.48 and 347.66, but since we need k to be should be the other way around, so k 7.48 and this one is minus 347.66. Yes, that's the correct one. So k should be between minus 347.66 and then 7.48, but since we need k to be positive, then k must be between 0 and 7.48. So that's the region that makes the closed loop system stable. Okay, problem number 5, the last problem. I have a closed loop system with unity feedback. So this is G of S, this is the output. We have error over there, and G of S is 1 over s squared plus 4s plus 20. And the question is, we need to find the steady state error. So find steady state error given U of S as a unit step. Okay, so we need to find U of S over U of S, right? Because if we know this U of S over U of S, then we can give U of S as a step input, and then we can use the final failure theorem, right? So U of S is what is U of S minus Y of S, right? And then this is over U of S, so 1 minus Y of S over U of S. So 1 minus the transfer function, so since Y of S over U of S is, we know that G of S over 1 plus G of S, and that one is 1 over S squared plus 4S plus 20 plus 1, right? 1 over S squared plus 4S plus 21. Then here we can substitute 1 minus 1 over S squared plus 4S plus 21. So 1 is S squared plus 4S plus 21 over S squared plus 4S plus 21 minus 1. So we have S squared plus 4S plus 20 over S squared plus 4S plus 21, right? And since U is a step, so 1 over S, then E of S is S squared plus 4S plus 20 over S squared plus 4S plus 21 times 1 over S. Hence, the steady state error can be computed through the final failure theorem. So take the limit as to 0, assuming that the closed loop system is stable, right? But we know that the closed loop system is stable because we have the transfer function, and the roots of the transfer function, they have negative real roots, right? Might be complex, but they have negative real roots, so we know that the closed loop system is stable. That's why we can apply the final value theorem. Remember that if the closed loop system is unstable, then we cannot apply the final value theorem, because the system is unstable anyway, so the steady state error will be infinity. So just keep that in mind. The final value theorem is limit s to 0 with s multiplied by e of s. So limit s to 0, s multiplied by this and this s and that, they cancel, so we are left with s squared plus 4s plus 20 over s squared plus 4s plus 21, and simply substitute s with a 0, we have 20 over 21. Alright, so that's the solution of the final problem, and that ends this recitation, and I hope good luck with the final exam next week. And if you have any questions, do not hesitate to send me email. All right, thank you, goodbye.